Hello everybody, and welcome to example 2. We are looking at the top of page 9 in the workbook here. This is going to be another example of a vector space, but this time a little bit more unusual of an example. Okay, so let's take a minute just to read this together. So they're giving us M sub m by n of R, and that new notation represents the set of all m by n matrices with entries in R. Now let's remind ourselves what this means when we say m by n matrix. So m represents the number of rows, and n represents the number of columns. Okay, and it turns out that this set is actually a vector space. Okay, you might find this a little unusual the first time you see this, because you might be used to thinking of matrices and vectors as being very different objects, but turns out that we can think of matrices as being vectors. They satisfy the 8 properties on our list of what it means to be a vector space if we define our addition and scalar multiplication in a sensible way. Okay, so to illustrate what I mean, let's just pick a specific value for m and n. How about m and n are both equal to 2, just to keep it a little bit small. Okay, the operations are defined as follows. Okay, so we'll take one 2 by 2 matrix that looks like this. Okay, and we need to demonstrate what we would do to add it to another 2 by 2 matrix. Okay, now, what do you think would make sense as a natural way to define this addition operation? Well, how about just using our definition of addition of 2 matrices? So we'll just add component-wise. So in the upper left-hand corner, we'd get A11 plus B11. Down here, A21 plus B21, and so on. Okay, just using the definition of matrix addition that we talked about in the last section. Okay, and then what about scalar multiplication? Well, we'll use the definition that we already have for that as well. Okay, so we'll take that C and just multiply it by every entry in our matrix. Okay, and we claim that this is a vector space with these operations, which means that we could go down that list of all 8 of those properties from the previous page, VS1 through VS8, and confirm that with this definition of addition and scalar multiplication, all of those properties would be true. Okay, now one question before we conclude this example: what would the 0 vector be in this vector space? Well, how is the 0 vector defined again? It's a vector in our space, so that if you add it to anything else, you get the same thing back again. So ask yourself, what matrix would we need to choose so that if we added it to just kind of an arbitrary matrix, we'd get the same matrix back again? If you think about it a little bit, just the 0 matrix, the matrix with all zeros, that would work. If you add that to any other 2 by 2 matrix, you're going to get that same 2 by 2 matrix back again.